Hi, section 7, electronic spectra and term symbols. Okay, electronic spectra of transition metals. Metals have partially filled d orbitals, d block, or f orbitals from f block in their atomic state or a common oxidation states. So the d block metal atoms, they ending with 3D, 4D, 5D. Whereas the F block ending with 4F, 5F are so lanthanides and actinides. So main groups or representative elements. Those elements have outer shell electrons in the S and P orbitals. If we see, of course, I will pass by these slides quick because they are just introduction and we presented these before. So as you see here, the main group of the metals, here are the non-metals, here are transition metals, and here we have the lanthanides and actinides. So main group metals and transition metals, there are difference between them. So if you react or dissociate sodium chloride salt, it will go to ions, cations of sodium aqueous solution and chlorine aqueous solution. So there will be the ions in the solution. If you dissolve NaCl solid in a solvent, and you will find, or you will result in cations and anions of both ions. But here, if you have the trichlorochromium plus 6NH3, you end up with this complex as a solid. Transition metals have filled set of 3d orbitals. We have the chromium 24, so we are ending with 6 electrons singly distributed. Copper 29, there are 9 electrons. Sorry, yeah, we have 9 and 2s. So the most stable is the 4s1 and 3d10. More stable. Orbital energies are not constant for the given atom, but depend on the way that other orbitals in the atom are occupied. So 4s and 3d orbitals have similar energies, similar look-alike similar energy. So 4s2, 3dn, or 4s1, 3dn plus 1. So you transfer one electron from the s to fill the d orbitals, and the remaining will be here 1, but this has been increased by 1. So they can like transfer electrons between them easily just for stabilization. So 4s2, 3d, how many? I don't know, is lower in energy, but for the chrome and copper, this electron configuration is more stable due to exchange of the energy. So there will be some energy exchanged, and there is an equation saying energy exchanged equals to n times n plus minus 1. That's divided by 2. So the n here is the number of unpaired electrons. Periodic table, as you know, so we have groups, we have periods. Okay. And of elements, and they are horizontal row of elements. Groups are vertical columns of elements. And we have here everyone is on electron configuration. So the periodic table, as you know, alkali metals, alkaline earth metals, transition metals, semi-metals, non-metals, and there is a halogen and noble gases. And the lower two groups are the lanthanides and actinides. So here, similar, so we can collect or select some of the metals are potassium, sodium, calcium, and some of the semi-metals here will be carbon or metalloids, silicon, boron, and the carbon and the rest will be the non-metals, and including hydrogen, oxygen, nitrogens. Transition metals will be in the middle. So you have the group number 1 from scandium to zinc, iridium to cadmium, lanthanide, and actinides. They are these groups, and extra will be the lower. Lanthanum series, they go from 58 till 71, and they are with 4f orbitals ending with 4f. So the size increases from the left to right. Actinum or actinium series, they are from thorium 90 till lawrencium 103, and they are 5f. So atomic size increase where when move vertically down, increase the size in the periodic table. Atomic size increase, move horizontally from the right to left. Ionization energy, the energy required to remove an electron from the element. So there is ionization energy in the groups from the lower to the top, more ionization from the right of the periodic table to the left, increasing the ionization. Oxidation states as well, we have like cobalt 2 remove 2 electrons. So we are ending with 3d7. When you remove the 4s2 and the cobalt 3, you remove 2 electrons from the 2s and 1 from the d, remaining d6. So the 4s is lower in energy, losing first. Transition metals are ionized, electrons are removed from the valence shell S first, and then from there you have the Z star effect is Z minus S. S is the shielding effect. Now we have here the nuclear charge increase, and 3d orbitals become lower in energy. Third ionization energy, 3 electrons removed. First ionization energy, 1 electron removed. So you see the increase here. 4D and 5D transition series, you have first, second, third series. So you increase atomic radii in nanometer. This will decrease the atomic number. Crystal forms and temperature effect. We have, if you add, this is the crystal ionic crystals of NaCl. If you add an increased temperature, they will fall down and lose the crystallinity. Similar here for the non-ionic crystals like copper, and they are very well arranged, but with the temperature they will fall and they will become non-ionic or melted crystals. So this is the melting NaCl, here the melting of the copper. Lanthanide contraction. We have lanthanide contraction effect. These are there is a contraction with these elements. 4f orbitals are buried into the interior of the atoms. The additional electrons do not add to the atomic size. So because we have big 4f, whatever you add of electrons, you won't increase the size of the atom. So the increasing nuclear charge causes the radii of lanthanide elements 57, 58 to 71 to decrease by an increasing atomic number. So lanthanide contraction, what do we have here? So in the lanthanoids group, separated by 15 additional elements, which are replaced by the atom of the bottom of the table, lanthani represent F orbital. So they are very diffused and do not shield well, because additional protons are now more visible to these electrons. So the atomic radius of a group 6 actinide transition matter is contracted enough to have almost equal atomic radii to group 5 transition metals, yttrium till cadmium. So now if you see here, maybe we can explain another slide. So now you have the protons of the nucleus. You know, the nucleus is positive charge, and there is electrons, the core electrons, and these are the valence electrons. So the core electrons, they protect the nucleus from the attack of the electrons. And don't forget the high spinning of the atom prevent destruction of the atom by electron to the protons. So there is a shield here of the core electrons. So the D and F orbitals contracted, electron move to inside, and then positive nucleus, core electrons shielding nucleus, valence electrons cannot attack the proton nucleus. And we can see here we have an increase in the melting and boiling point from the right to left, left to right. And we have the melting and boiling point in the lanthanum group and actinide group from the end to the middle, from the left to the middle, an increase melting point. General decrease from left. This is the physical properties, melting boiling point of these groups of F groups. And we have here a general description of physical properties for the second row D block. You can see this is increasing from here, from the middle to the right. Increase atomic radius from middle to the right, and from the middle to the left. Increase radius. So now we can conclude that it's not always you increase number of electrons, you can increase the size of the atom. That's not accurate. So it depends, and it's been found that adding more electrons sometimes in elements, they don't increase the size of the. So sometimes adding, yes, increase, sometimes reduced. Physical properties of the third row, similarly. See the second row, third row. They are typical. Sample questions you can find here. And I just mentioned structure of the cisplatin, carboplatin. Why are important in medicine? They are anti-tumor agents and they use in dental teeth treatment. This is cisplatin, 2 chloride, 2 ammonia, and it's a square planar. Carboplatin, you can see this is the carbo and 2 nitrogens, but the oxygen, the chlorine being replaced by the carbo group. Here are more questions. Define lanthanide contraction effect. You can find it here exactly. So there is a not destruction for the atom because of the core electrons shield the nucleus protons from the attack or attraction from the negative charge of electrons surrounding. So the atom is safe. Electronic spectra of transition metal complexes. You remember there is a ground states and there is excited states. Visible area, ultraviolet regions of the spectrum that is between this and this, those in which electronic excitation usually occur. So there will be some excitation if the energy in the visible and the ultraviolet between 10,000 to 50,000 cm-1. So light of these wavelengths may be absorbed by a complex for a variety of reasons. There is ligand spectra. Every ligand, because has electrons, so we can find spectra for such ligand. So water can absorb bands normally in the ultraviolet. And these bands remain in the spectra of the complex, but may be shifted somehow from their original positions. We have some liquid water absorption spectrum across a wide wavelength. So this is the water. This is the absorption. And then you can see the spectra of water. We need this spectra when we characterize a sample and see if there is a water present in the sample when tested by infrared or other techniques. So there are 3 principal types of ligand absorption. There is N to sigma star transitions. Electronic transition describe promotion of electron from non-bonding lone pairs N orbital to an anti-bonding sigma orbital. Designated as sigma star, such transition generally involve high transition energies, appear close to a mixed with Rydberg transitions, the water example. So now, you remember I told you that we always have to draw the empty orbitals of any ligand or complex. Why? Because maybe any of these electrons can absorb energy and go to the higher energy level. When to go to the higher should be empty. Okay, so this lone pair can absorb energy and jump to the sigma star antibonding, which are empty. And this energy given to the water can absorb by lone pairs and go upper energy level and show a spectrum when it's come back losing this energy. So there were lone pair. This is the first time we see the lone pair jumping to the antibonding. N to pi star transitions. We can see here carboxyl or alkoxyl. So COR2. So here we have transition can occur in molecules containing atoms that are involved D in pi bonding. Also contain non-bonding electron pairs. So we can see this in aldehydes, ketones, which contain double bond between carbon and oxygen group. So these double bond here, you can see on the diagram here, they are double bond and involved, there will be 2s2 non-bonding, not involved in any bonds. So they can be used to do sigma bonding to the metal. And the rest you can see between the oxygen and carbon. Carbon here is 4 electrons, 2s2, 2p2. Oxygen have 4 electrons in the valence shell, 2s2 and 2p4. So this one not involved in bonding, and the other one, you can see there is a pi bonding between P and P. And here, the rest, you see 2 electrons with 4 electrons will do 6. This one is non-bonding, and as a lone pair, and then 2 by 2 will be 4 electrons in pi, because it's pi and pi, so it will be pi bonding. And these will do the double, and then leaving the anti-bonding pi star empty. So what we have here, we have 1 sigma, 1 pi, and then you have a lone pair there. So the non-bonding electrons are in level higher than the sigma and pi bonding level, but now the lowest unoccupied level is a pi star level. The lowest, we call it lowest unoccupied, so this is the LUMO. And its level is the pi star. This is the LUMO. Why we call unoccupied? It means it's ready to receive lone pairs from other orbitals. So the transition of the lowest energy is N to pi star. So from N, from the lone pair, to the pi star, this is the transition, and this will do a spectra in the visible region. Pi to pi star, we have transitions. Okay, so once you have pi, it means filled with electron. When you have pi star, it means empty. That's how to move electrons. So molecules possessing double or triple bond, but no transition atoms with non-bonding electrons, D0, have the pi bonding orbital as the highest occupied. This is the HOMO, and the pi star orbitals at the lowest unoccupied level. So now the transition thus will be pi to pi star, because this occurred in olefins, dienes, aromatic system. So now we have pi electrons, they can immigrate to the pi star empty. Where can we find this? In aromatic, double bond, triple bonds, so on. Pyridine can have both N to pi star and pi to pi star. So from the lone pair to the unoccupied pi antibonding, or from the pi to the pi antibonding. You can see here, this is the pi, and this is it's above the ring. This is the pyridine ring. You can see pyridine ring. There is nitrogen, and there is empty pi star and filled pi because of the delocalized pairs of, or 3 pairs of double bond. So they will be delocalized and they will form pi. They have pi electrons. So imidazole have double diene. This is the opened diene. This is one or double bond, and this is the benzene ring. So these are can form pi to pi star transition, and they will give a spectra. There is another spectra by the counter ion. This is the first time we discuss the counter ion spectra. And every part of the complex have spectra. So there are many simple anions do not absorb radiation in the visible or ultraviolet regions, like halogen, sulfate, perchlorate. Only perchlorate does not form from stable complexes with metal, does not form. Only perchlorate does not form stable complexes with metal ions. So to increase spectrum of hexaqua ion H2O by 6, the solution must be acidic to prevent hydrolysis. So perchloric acid would be suitable acid to add. The spectrum of titanium hexaqua titanium 3 obtained in perchloric acid, but in hydrochloric acid is used the position of the band maximum move to lower wave number or long wave number, as species such as penta aqua chloro titanium 3 becomes important. So many oxo and ions such as NO3 minus, NO2 minus have intense absorption in the ultraviolet. So where can we see this spectrum? Could be in the visible region, in the IR region, in the ultraviolet. Each one depends on the ligand or the counter ion. We have something else called charge transfer. And charge transfer, there is a spectra for it as well. So these transitions take place between molecular orbitals and metal and ligand orbitals. Between molecular orbitals of a metal and ligand. You remember the donor and back donation, so you can see this as a charge transfer. So from metal to ligand will be M to L, that's oxidation, or transfer electron from the ligand to the metal will be reduction. So metal will be reduced if accept charge from the ligands, and the metal oxidized if lose electrons to the ligands. So charge transfer are intense absorptions, usually located in the ultraviolet, but frequently in the visible region. So examples we have here, D0, titanium 6 chloro, losing all 4 electrons to become D0. Chrome, CO oxide, you are losing all the 6 electrons to become D0, and D10 compounds such as mercury, which lost 2 electrons from the S ending with H, or D10. There are 3 types of charge transfer. Let's check how many types we have. There is ligand to metal charge transfer, LMCT. We call it from ligand to metal. So it will be reduction of the metal. And we discussed this, but we give it to this, these letters. LMCT means ligand to metal charge transfer. And we can see this in the halogens. So they transfer lone pairs to the metal, and the metal will be reduced. We have spectra of the hexahalogen have been studied in details, and then we will show you some figures, energy level diagram. So if the sigma and pi are filled with bonding electrons, while the sigma star and pi star are empty or vacant, 4 transitions are expected. If you have sigma star, pi star, so you expect transitions, either pi to pi star. This is from the T to G, or sigma to sigma star. But you can see pi from the EG to pi star, and sigma to sigma star from the EG. So the EG transferring electrons pi to sigma star, sigma to sigma. T to G transfer pi to pi star. So everything will go to the pi star. So the energy of the pi to pi star of the T to G transition decrease in order of these. Look, we are changing the metal, with the same oxidation number, and you can see there's a change in the energy. Why? It's due to pi star. Whatever spectrum you need energy for it. So depends on the metal ion. And here we can see what we're talking about is the T2G to EG transition DD. You remember for the color? This is responsible for the color. When there is a moving of single electrons from T2G to EG, so it will show the color. So we have here metal to ligand charge transfer, MLCT, metal to ligand. From where? From T to G. So here we have ligand pi orbitals. So the ligand should have pi star empty, pi star empty, and the metal should have sigma EG star, T to G star empty. So you can transfer from the pi or sigma to here to the E star, EG star, T to G star, or you can transfer from here to empty orbitals of pi star. It will be metal ligand charge transfer or ligand to metal charge transfer. So here, moving electrons to upper energy level, it will show you charge transfer spectrum. Absorption species containing pi and sigma and n electrons. It means lone pairs. So here you can see n to pi star. It means lone pair to the pi star. You have lone pair to sigma star, we have movement of pi electrons to empty pi star, or sigma occupied orbitals to sigma star empty. So every star is antibonding. See, antibonding sigma star, antibonding pi star. But when you have n, this is a non-bonding pairs of electrons. When you have a bonding is a pi, or sigma is a bonding. A trend of ligand to metal charge energy, transfer energy. If you have oxidation number 7, so you have an rhenium bigger than tactinium, bigger than manganese. You have tungsten F plus 6. Here is a plus, tungsten plus 6, more than molybdenum, more than chromium. If you have oxidation number 5, for titanium will be bigger than niobium, bigger than vanadium. So the energies correlate with order of the electrochemical series for the elements. So metal ions, most easily reduced, correspond to the lower energy transitions. So this is consistent with the result of the practical calculations. Ligand to metal, look, permanganate, very strong, can transfer its ligand to the metal. And here, color, artist pigment, cadmium yellow, due to transition of pi. This is from the pi sulfur to the cadmium 5s. This is the ligand from the from the sulfur to the cadmium, so it's a ligand to metal. Here, permanganate, so we have charge transfer from the oxygen to the manganese, moving, and from pi. Here we have the sulfur to mercury, pi. Sulfur has pi. Mercury has S, empty. Iron oxides, they are red and yellow due to transition from oxygen, pi, to iron 3D. So wherever you have empty orbitals, you can transfer from these all S, O, O, these all, they have pi orbitals. So they can transfer their electrons to the empty orbitals of cadmium S, mercury S, or in the D of the iron. Metal to ligand charge transfer. So you have here, as we talked about, bipyridyl. If you have empty orbitals in the antibonding of the ligand, so you can transfer electrons from the metal to the ligand. So the ligand has to have pi star empty. So you can see from T to G, transfer to the pi star, from EG to the pi star of the ligand. Metal ligand, metal to ligand charge transfer, you can see here the color bipyridyl, and here we have the ruthenium 6 coordinate and chlorine by 2, so oxidation number will be 2, and you can have pi star and C triple bond O, C triple bond N, SCN, all of them, they have pi star, so you can transfer electrons from the metal T to G to them, to the pi star. And here the transition, as you see, from pi to pi star. from pi to sigma star. This is the metal to ligand charge transfer. We can see them here. Metal to carbon bonding. Metal to carbon, you can transfer between metal to carbon. Carbonyl ligand is a pi acid. Why pi acid? Means carbonyl receive electrons. This is pi acid, so losing electron, oxidized. Acid in the loose sense receives electrons from the metal ion, is a pi acid because this involves pi bonding. Pi bonding. Overlap between the pi star orbitals of the CO and the d orbitals of the T2G. So there is a d pi to pi bonding. Structure involved in the pi acid nature are those. And this is we explain carbon oxygen, triple bond. One of them is pi filled with electrons and the other one cloud of pi star empty, can receive electrons from the metal. So from D to pi star overlap. So what stabilizes the CO complex is the metal to carbon pi bonding. Because we said pi star is empty. So this stabilizes the complex. IR spectra and metal carbon bonding in carbonyl complexes, you can see here, decrease in the double bond. Here is increasing in the double bond. Once you have these complexes, you see the frequency of the IR, for the carbonyl, 1748. And for this carbonyl, here carbonyl can be shown in the 1858 centimeter minus 1. So all these we depend on when we do the IR spectra for any solid sample of the material or of the complex. So you can find to characterize where is the spectrum present, where in the region of the IR region. So this is carbonyl of the chrome, different, you see 1800 here, 1900. So you can identify which metal is present in the sample. Is it titanium, vanadium, chromium, manganese, or iron? Depends on the band appeared in which region of the IR. Similarly, double bond, you can find it between this and this. I remember when I was doing my samples, I prepare the sample, then analyze them. I had to do the IR disk, the hard disk of the IR. We call it KBR, IR KBR. So you remember, or we prepare the disk first and then put it in the IR machine. And then the IR beam will hit the disk of the compound mixed with KBR. And then we'll see the spectrum. The spectrum will show me the peaks. Each peak is characteristic to a specific, like bonding. Is it belong to carbonyl? So I know where this, and all these numbers, we can find them in the textbooks to do the practical testing or IR result or test. So if there is a triple bond, we can find a peak between 1850 and 2100. If I have double bond carbonyl only with two bridges of the metal, so it would be a bridging carbonyl, so I can find a peak between 1700, 1860, and so on. So every peak in a region, if I see the peak in a region, I can say this is a triple bond or double bond. Is it a carbonyl, a bridging, or it's a single carbonyl to one metal? So as you see here, this is the IR spectrum, and this is the peak as I talked to you about. So this peak is for the bridging carbonyl, whereas this peak is the free carbonyl. So look, this is between 1800 and 1850. Here is between 2000 and 2050. These are different peaks. Each one characterize or identify, is it belong to a bridge or belong to free terminal carbonyl. So metal to metal charge transfer, metal to metal. Now this is the third one. So we did ligand to metal, we did metal to ligand. This is the third one, metal to metal. Do we have such a thing? Yes. We can see if you mix Prussian blue, there is 7 iron, 18 CN. And the iron here, two types, iron 2 and iron 3. In the formula, you can see there is a complex here and there is a counter ion here. The complex is 6 cyano iron 2, and outside is the potassium iron 3. So here between the iron 2 and iron 3, there will be a charge transfer. And so intravalence, when there is an intravalence, charge transfer can occur. Intra means different. Inter will be similar or inside. So intra will be outside. And here are the orate or gold. And you can see there is a bridging chloride and there is a free or terminal chloride. So how can we characterize each? We call it black gold compound. And this is charge transfer is intravalence electrons, means between orate 1 or 83. So because they are different oxidation number, so you can see a charge transfer between them. And here, color charge transfer complexes, where so you have different color, each color associate with a different halogen. Anyway, so you have iodine, PPH3 charge transfer complex in dichloromethane. So iodine, sample number 1, where is it? What? This one. So this is sample number 1. I have to separate sample number 1, and here is number 3, colorless, and number 4 is blood. So sample number 1, there is iodine in dichloromethane, so no charge transfer. Few seconds after excess of PPH3, charge transfer occurred. 1 minute later, excess of PPH3 add charge completely been formed. And number 4, immediately after excess of iodine was added, contains iodine. So this is been obtained from Housecroft and Sharp. So identification of charge transfer color, sulfatochromism, intensity. So if you see the color change, there is a charge transfer, and there is donor acceptor. Sulfatochromism in solution transition energy, and therefore the complex color varies with variation in solvent. So this is due to solvent. They call it sulfatochromism. So if there is, you change the solvent, maybe there is a change in the charge transfer. Intensity, the absorption bands are intense and lie in the ultraviolet or visible region of the spectrum, and so on. So how can you identify charge transfer bands? You depend on color, solvent, and intensity. Ligand field spectra, Russell-Saunders term symbols and states. So we talk about this for the next video.